I was asked to look at problems 22 through 24 in section 3.8 on Achieve with you, and I can definitely understand why question 22 was asked. It's similar to my book homework problem number 47 if you want to go back and look at that one as a reference point as well. But let's go ahead and look at this one together. This was the problem I had on Achieve. It was to take this relation curve equation and try to find the point xy such that the horizontal or the tangent line would be horizontal at that point, which just means its derivative dy dx is going to equal 0. So I knew I needed to solve for dy dx in the problem. I go ahead and I take the derivative with respect to x. Derivative of x cubed is 3x squared. Derivative of y cubed, 3y squared times dy dx. On the right hand side I had to use the product rule. Derivative of the first is 23 times the second y plus the first 23x times the derivative of the second dy dx. Now I gathered my two dy dx terms on the same side. I said I'm going to factor out a dy dx, and when I do I'll have 3y squared minus 23x left over. On the other side you already had a 23y. I'll move over the 3x squared, it becomes a minus 3x squared. Okay, now, at that point, I go ahead and say, well, my derivative is equal to what I had on the right divided by what was previously multiplying the dy dx. So I have my solution dy dx, but we're still far away from the answer to this question. Because now I need to try to find a way to set that derivative equal to 0, because that's the only way that I can guarantee that the function will have a horizontal tangent line. Horizontal lines have a 0 slope, thus a 0 derivative. Okay, so if I try to set that derivative equal to 0, it's really not as hard as you might think, because the only way a fraction can equal 0 is if the numerator of the fraction equals 0. Remember, the denominator doesn't make it equal 0, it would just make it not exist if it was 0. So the only way that fraction can be 0 is if the numerator of the fraction is 0. So I set the numerator equal to 0. I'm going to solve for y. So when I solve for y, I move the 3x squared term over. I divide it by 23. So what I know is that I will have a horizontal tangent function if and only if y is equal to 3 times the x term squared divided by 23. So that's not really that helpful in and of itself, but what I can do is I can take what I know y must equal in terms of x and plug it into the original equation. So everywhere I see a y, I'll put 3x squared over 23. That's what I've done right here. So now my original equation becomes x cubed plus 3x squared over 23, quantity cubed, is equal to 23x times y, that's now 3x squared over 23. And now I need to solve for what x needs to be in order for this to occur. So on the left hand side I left the x cubed alone, and then I'd have 3x squared cubed. Well, 3 cubed is 27, x squared cubed, x to the 6th. I used my calculator to cube 23 to the 3rd power, that's 12,167. Now on the right hand side, a lot simplified. Notice the 23's cancel, and you'll just have 3x cubed left over on the right hand side. Then I notice I had common terms of x cubed. I subtracted x cubed on each side. That left me with a 2x cubed on the right. At that point, I saw that I had a x on both sides, so I just said, well, why don't we just go ahead and divide both sides by x cubed? That makes it much easier. On the right now you have 2. On the left, if you divide by x cubed, that's just an x cubed there. You still have your same coefficient multiplying it. But now I can say if 27 over 12,167 x cubed is equal to 2, then x cubed is equal to 2 times the reciprocal of that fraction. So in other words, times 12,167 over 27. Now if x cubed is equal to this, then I know I should be able to solve for x by taking the cube root on each side. So I say, well, the cube root of the right hand side. Now, I remembered, well, 12,167 was nothing more than 23 cubed, so the cube root of 12,167 is nothing more than 23. So I said 23, and I'll also have the cube root of 2 in the numerator. My denominator is the cube root of 27, which is just 3. So that made for a nice exact answer there as opposed to an ugly decimal. Now, I know what x is, so I can go back and solve for y. Recall, y was equal to 3x squared over 23. So then I can say, well, okay, then y is equal to 3 times this x term, 23 on the cube root of 2 over 3, quantity squared. You're plugging this in for x there. And so then I can say, well, then that denominator has to be 23 still. Now, when I square out this fraction, 23 squared over 3 squared, and then the square root of 2 is just, sorry, that's the cube root of 2. The cube root of 2 squared, that means the cube root of 2 times the cube root of 2. I wrote it as the cube root of 4. I left the other squared. The reason I left that 23 squared in particular is I knew one of the factors of 23 would cancel with the denominator. And then I can say I just have a 23 to the first power in the numerator. I'm going to have 3 divided by 3 squared. Well, I know I have a 3 in the denominator then. And that cube root of 4 is a factor in the numerator. So I get a final answer for y of 23 on the cube root of 4 over 3. So then we know the point at which the tangent line is horizontal is this ordered pair, the x value that we found in this step, and now the y value that we found right here, our x and our y for the 23 root of 2 over 3 and the 23 cube root of 4 over 3. And if you're thinking that that's a gorgeous problem, you're thinking like me. Now, up next, the other problems aren't nearly as hard, or at least as long, in the rest of this section. 23 is asking for the second derivative. You can't take the second derivative without taking the first derivative. So here I was asked to find the second derivative of y with respect to x twice, and then it told us just to call it y prime and y double prime for the two derivative answers. So when I take the derivative of y to the 13th, I get 13y to the 12th dy dx. When I take the derivative of 13 over 2x squared, of course the 2 comes down in front and you just have minus 13x to the first. There is nothing else because the other term here would be dx dx, and we know that's just a factor of 1. Derivative of any constant, 0 on the other side. Now I solve for dy dx by moving the 13x over. It became positive 13x, and then dividing by the coefficient of dy dx. That goes to our denominator to become 13y to the 12th down there. Of course, our 13's cancel, and our first derivative answer is just going to be x over y to the 12th. For our second derivative, I'm just going to use the quotient rule on that. So I can say, well, quotient rule would tell me to square the denominator, then bring that denominator to the numerator times the derivative of the numerator. Derivative of x with respect to x is 1. Minus the numerator x, now times the derivative of the denominator. So you'd say, well, that's going to be 12 times a y to the 11th power. And then you'd say times the derivative of y with respect to x. But instead of putting a dy dx there, I said I'm going to go ahead and put what I know it's equal to. That is dy dx. So I substituted x over y to the 12th in for the first derivative there. And then I just needed to simplify. I knew I didn't want to have a fraction inside of a fraction, and I have a y to the 12th in the denominator in that fraction in the numerator. Well, it's being multiplied by y to the 11th, so it's almost already gone. But I just need to multiply by one more power of y, and I'll do that in both the numerator and the denominator. And when I do that in the numerator, it's going to give me a y to the 13th, and the y's cancel in this second term, and I would just have minus 12x to the second. In my denominator, I'd have a y to the 24th times y for y to the 25th, and then I would say, y, that's my final answer for the second derivative. I'm happy with that one. Now, last one here, and this is a good precursor to where we're going. So In the earlier problems, you were always taking the derivative with respect to x, and you say, well, the derivative of x with respect to x is just dx dx, and you never have to do anything for that. It's just a 1. But now in 24, it's saying all functions, or all variables, I should say, are functions with respect to time. So you can't just discard a dx dt or a dy dt. They're not equal to 0. They're not necessarily equal to 1. We don't know what they're equal to, so we must account for them in the problem. So it's telling us to take the derivative with respect to t of this original relation. So I look on the left-hand side and I say, well, it's going to require the product rule. And I'm thinking, okay, the derivative of the first, the derivative of 5x. Now, if I were taking the derivative with respect to x, it would just be 5. I'm not taking the derivative with respect to x. I'm taking the derivative with respect to t. So I say, well, it's 5 times dx dt, and I don't know what dx dt is, so I have to leave it there, times the second, plus the first, 5x, times the derivative of the second, and the derivative of y with respect to t, I don't know what it is. I must leave it in there. Equals the derivative of any constant with respect to time. Well, constants don't change, so again, their derivative is 0. Now I needed to simplify, and it was supposed to solve for dy dt, so I just moved the dx dt term over, and it became a minus 5y dx dt, and typically we put the derivative at the end, although the order of multiplication really doesn't matter, it just looks better. And now I needed to solve for dy dt, so this was 5x times dy dt, so I was divided by 5x on both sides. So I had negative 5y over 5x times dx dt. Simplify that by canceling out a factor of 5 to negative y over x times dx dt. Final answer there. And this is a very good precursor to our next section, which will be talking about related rates, or actually that's section 310. So we have one more section before that. But it's gorgeous stuff, guys.